Welcome to the 9th lesson in our engineering design process series. Today we'll be talking about assembling and evaluating the final design solution that we've developed for our particular design project. I'm Denny Davis and I'll be leading the discussion today. As you recall, we've progressed through most of the design process. We've gone through problem definition, conceptual design, prototyping, and testing. Now we're on to the final assembly and then evaluation of the design solution that we've come up with. We're going to be talking today about how we assemble this final solution, and then also about how we're going to evaluate that solution. Remember that when we're assembling this final solution, we're talking about using final components. This is not just the temporary components that we used in prototyping, but these are the final components that we would use in our final solution. We're also assembling now to perform as specified. As we said, we wanted the solution to perform. We want to be sure that our final solution has all the required features that we said it would contain. And we're also then making sure that it's ready to be tested. We want to rigorously evaluate the solution to make sure that it's ready for use. As we evaluate this final solution, we ideally are going to be testing it for a certain set of users, but it's also great if these intended users are involved in the testing process so that we're seeing how they utilize the solution. We're going to be duplicating conditions that we expect for the actual implementation of the solution. So it's best again to have something that duplicates where we expect this solution to be used in the end. We're coming out of this evaluation process with proof of performance. We need to be able to prove that the solution meets the performance expectations that we had identified. Ideally, this performance, the proof of this performance is going to be adequate for ourselves or other outsiders to make a judgment. Is this solution ready to be implemented, or is it disapproved, so that we have to go back and repeat some of the earlier steps before it will meet the requirements that we had identified. So this is a critical stage in our design process of ensuring that we've produced the final solution and we have the evidence that it meets our expectations. So let's first take a quick look at some of the things we should consider when we're assembling this final solution. General considerations might fall into a number of categories. First of all, considering whether we're putting standard parts into the solution or whether these are custom parts. As you might imagine, customized parts are going to be more expensive, maybe more difficult to maintain. It also probably will take more time to obtain or manufacture these parts or obtain replacement parts if they need to be replaced. So standard parts have some real advantages for us. We also need to take real care in the way that we manufacture or assemble this final solution. We're often drilling and cutting, and if we have errors in what we're doing, this is going to cause some real challenges in our assembly process. The old adage of measuring twice, cutting once is so crucial here. make sure that we've done it right so that it will assemble properly. We want to consider the right kinds of fasteners that are located so we can access them as we need to. They provide the strength for fastening. They're removable, or perhaps we need them so that they won't loosen over time. So we need to consider the fastener and how it's implemented. And also, will this solution, when put together, will have the freedom and movement that we expected? Are the joints that are to be rotating able to rotate? Those that are intended to slide, do they allow sliding? Those that are to be rigid, are they rigid? We need to carefully consider these things in our manufacturing. We also need to consider what materials we're using. Sometimes we have options, so we need to think about the wear, friction that might be associated with these materials, the cost, whether it's initial cost or replacement cost, the weight and strength of these materials. And in some cases, where we have potential for building up static charge, we need to be careful in selecting materials that will minimize electrostatic buildup if we're concerned about discharge that could disable our robot or whatever our system happens to be. Some other considerations during the assembly process include appearance. Now we can make something that's really lovely, unique, stands out. It's clearly something that we have created. That can be important to us, but we need to be careful that we don't invest too much time and too much money into that. We should also consider flexibility. Is our robot, in this case, constructed in ways that we can make adjustments? We can easily replace parts. Perhaps is it modular enough so we can take out one part and put in a substitute part? So think about the flexibility that would be useful for this robot. Make sure you have considered that in your assembly process. And final, safety. Of course, we don't want any sharp points or edges that could injure operators or people who are maintaining it. We also need to think about safety for things that are vulnerable, like the wires, electronics. Make sure that we have assembled them in such a way that they're protected from damage. And also, such as robots in competition that need to go through inspection, we need to make sure that we have met all the requirements, all the criteria that have been defined for us to be able to participate in competition. Let's not forget that we had established a whole set of solution requirements earlier in the process. So one of the things that we want to check off before we proceed is, have we dealt with these solution requirements adequately? Have we met them? So remember, we had functional requirements, perhaps speed, accuracy, things that we said that the robot must be able to do. Have we provided a solution that will meet these requirements? There are certain technical requirements in terms of durability, its ability to be repaired and replaced. Have we adequately addressed these? Let's think about that as we assemble this robot. What about the resources that are consumed in this design? Have we chosen the right materials, parts that are available and cost-effective? What about those that we're going to be manufacturing? Do we have adequate time and access to equipment for manufacturing and custom parts? And finally, the human requirements, safety, as I mentioned previously. safety in manufacturing, when we're repairing, when we're operating, and also just the human factors, the way in which the operators interact with it. Is this really smooth and effective to make our design really effective? So you can see that based on the requirements we defined earlier, there are some things we need to keep in mind as we complete this assembly process. Also, since the next step is to evaluate this, we need to make sure that we have prepared the final design so it can, in fact, be evaluated in realistic conditions. Of course, we're going to identify critical questions that need to be answered, perhaps scoring success, time for certain functions to be accomplished, accuracy in which we accomplish the tasks that are before us. And associated with these kinds of questions, we're going to need to take some measurements. So we need to be thinking ahead about what measurements are going to be needed, what times, what scoring, what other observations might we need, because this will then drive resources that we need for this evaluation process. We need to make sure we have the instruments or measurement devices on hand that are going to be necessary for taking the measurements. We need to have the space, the physical arrangements, the field, the equipment, whatever is needed so we have a realistic test condition. Do we have adequate time for the setup and testing? Do we have the personnel available? We need to be sure that all these are available so that when we get ready to do our evaluation, we can complete the job and do it well. I'm going to suggest here that we have a template. This template includes certain components, certain kinds of information that you'll want to have defined for any evaluation process that you're going to implement. First of all, we need a name for this test that we're going to be using. Descriptive name, so we know just by looking at it what it is, so that we or another reader can easily look at it and know what this evaluation is all about. Associated with that, we have a date which the evaluation is occurring, and the individuals involved as recorders or assistants or whatever. We also need to identify the experimental questions. Again, thinking back to our requirements, what are the questions that need to be answered by this test in order to give us the assurance that our design is adequate? Once we've identified questions, we need to define the procedures that we're going to use. And associated with procedure, usually you have a setup where drawings, photos, sketches is very valuable to help communicate what this procedure is that we're using. And also, what are the variables we're dealing with? What things will be held constant? What things will be varied during our testing? These need to be clearly defined. Then, as we begin to gather data, it's always handy, useful to have a table or a data sheet so that we have identified what data must be collected, we have room for it, and we don't have our notes on little pieces of paper that get lost. In addition to the data that's collected, we're going to need to be sure that we then summarize and analyze this data, keeping in mind what the questions were that we're attempting to answer here. And finally, discussion of what we found from the analysis and conclusions. These conclusions then refer back to the questions. From the data, what are the answers to the questions that we posed, that we were attempting to evaluate and answer in this particular evaluation process? So this template then gets us started thinking about what we need to document as part of this evaluation process. Let's take some examples. The first example is one about the scoring. Let's assume that we had stated that our success in scoring points on the 30-point peg would be a certain success rate, but also would be accomplished in a certain period of time. So therefore, a test would be, let's find out what the scoring success and elapsed time are for this kind of scoring. So what would the questions be here? Well, the first one would be, what is the ring scoring success for this 30-point peg? And the second one, how much time is required, or how much time elapses in the scoring? And you might want to break that down into the different steps in scoring. In this case, time for collection of the rings, transportation across the field, and then actual delivery onto the peg. So these two questions then guide what we're attempting to learn from this test. We develop a procedure then. Step one here is define where we're going to put the ring. Number two, where are we going to put the robot? We need these to be consistent so that we have data that we can say fits a certain test condition. We then run the test. We record the time for ring collection, for its transit over to the site where the goal is, and its delivery onto the peg. We also then record the success in scoring. And ideally, we're going to be observant and note failures or unusual circumstances that we encounter and record those as well. So this basically gives us a testing plan for this particular evaluation. All right, with that plan in mind, we're going to collect data. So we have a data sheet which has a place for the time for collecting, time for transit, time for delivery, points scored, and then notes or observations. And we'll do this for multiple runs. Let's say in the first run, it took us 3 seconds to collect a ring, 4 to transit across the field, 3 for delivering it onto the peg, and we've resulted in a 30-point score. It might be noteworthy to say that, this first test, the operator seemed to be very hesitant in their actions. So it's a good note to make here. Let's look at the second run. Perhaps we have 3 seconds, 5 seconds, 2 seconds. And note that the transit time is a little bit larger here, but also note that we missed the peg and have 0 points scored. So a note here with regard to what caused that, what kind of a miss is useful. Here the operators misjudged their distance from the peg when they attempted to score. So the other runs, we would have similar kinds of time recordings, scores, and notes. This would be important for many runs as we complete. Now, what kind of analysis would be useful to understand what the data says? Well, number one, points scored. Note that for each of the 10, let's say we had 10 runs, we had 2 times when we did not score. So we can tell from this that 80% of the time we scored. Now looking at the component, time components for these different collection, transit, and delivery steps, we begin to see how these total times vary and also how the time for the components vary. So this is very useful for us. Now, thirdly, if we sum up all of these 10 runs and get a composite, we begin to see where most of the time was consumed. Shown from this pie chart, we see that 43%, or the largest portion, was in transit, and the other collect time was 31%, the actual delivery time 26%. So these graphs give us good summaries to interpret what happened. Now let's discuss those, see what we learned from the test, and make some conclusions. The test data showed us, first of all, that the attempts at scoring 30-point scores were 80% successful. The total scoring time varied from 8 to 12 seconds with a mean of 10 seconds. Collection time varied from 2 to 5 seconds with a mean of 3.1, and so on. So we've identified here the critical numbers that relate to the questions that we posed. What are the conclusions that we make from this? Number one, scoring success, which was 80%, is acceptable. It's within the range of what we had intended for a robot to be able to achieve. Scoring time, it varied quite a bit. We could see that the total scoring time ranged from 8 to 12 seconds. That's a 50% variation, which would be of concern. So it tells us that perhaps we need more operator practice to trim down that variability, but also it may suggest that if we could automate part of this where there's the greatest variation, that could be of great advantage to us. So from this test then we can see how well we met our requirements, but also learn the kinds of things that might lead us to some additional improvements over time. Let's take another example. Perhaps we're concerned about the durability of a robot. So what would questions be in this case? Perhaps what are the most common robot failure modes? Okay, well, how does it fail? And number two, what are the root causes of these failures? In other words, what really caused the failure to occur? Let's define a procedure that will help us answer these questions. Number one, the drive team conducts an inspection and makes adjustments. This is similar to what you'd expect before a competitive match. Then the drive team conducts a game run for the entire game period, so they're simulating what would happen in a match. The recorder documents any failures that occur. And then after the match is over, the drive team identifies the impact of each failure and what they believe is the root cause for each failure. Now we'll repeat then the same process for, let's say, 10 different game cycles so that we have enough opportunity to test variability and see what kinds of failures occur. So this is a procedure that we could use. So the data we would collect then would be for each run, what failure occurred, impact of that failure, and cause of failure. Let's say that for the first failure that we saw, the robot turned the wrong way in autonomous. All right, we have to stop and ask them, what was the impact of that? Well, if the autonomous action was to score 25 points but turned the wrong way, we missed that opportunity. It could also put our robot in a bad position for the next period of the game. Think then about the cause. In this case, it was probably a program logic error. So we've identified for the first failure. Let's look further. Oh, another failure occurred in the same run. The ring fell from the hopper during transit. So the ring had been collected as the robot moved across the field. The hopper was bouncing, and that caused the ring to fall out. The impact was that the driver had to go back and collect the ring again, so it's a loss of time. So we could then look at a second run, identify the failure, the impact, the cause of failure, and so on. The third run again, we could do that. So going through 10 runs or whatever number we're able to accomplish, we can then gather this kind of data to identify the kinds of failures, how that impacted us, and what the root causes were. This then could be summarized by some graphs of this nature. First of all, in what game segment did the failures occur? Here we've identified them by the autonomous game period, the normal driver-controlled period in orange, and the gray is the end game period, the last 30 seconds. We can see clearly that the largest number of failures occurred in this driver-controlled period. Points lost, in other words, impact, that was in terms of points. We could plot those and see what kinds of costs we were incurring from these failures. And then another important approach is to kind of cluster these failures into groups. How many of them were really operator errors? How many of them were programming errors? How many of them had to do with the transit process, electronics, and so on? So we begin to cluster them into groups, which helps us then identify where are the greatest failure occurrences where we should put some more attention to prevent these failures in the future. So we're leading now to the discussion of the results. The test data showed that, number one, over half the failures occurred during the operator control period. If we also consider the end game, which also has operator control, we have nearly 75% of these failures occur when the operator is really in control. Number two, nearly all failures resulted in a decrease in points scored. Most frequent causes of failure are operator error, programming error. So then from these kinds of observations, we can make some conclusions. One, failures definitely reduce points scored, and this can cause us to lose a match. So that shows the seriousness of these failures. Operator training and practice are vital to preventing failures because we saw that a large number of the failures were operator related. Programming errors are also a major concern, and these can be avoided if we've allowed time for adequate testing of the programs. Number four, some of the robot function and operator cause failures might be avoidable if we were to develop control systems to automate some of these actions. So if we're seeing significant numbers of failures occurring that could be controlled by automating, this may justify our putting some effort into making some modifications to our robot. Let's look at a third example. If we are looking at controlling travel distance, and this could be where we want the robot to travel a precise distance across a field, stop, and perform a particular function. We need to determine the parameters that give us the precise control that we want. So, what are the questions here? Number one, what's the best proportional constant for rapid, accurate 2-meter robot sprints? So we want the robot to travel 2 meters and stop very accurately. What's the proportionality constant that will best give us that kind of performance? And secondly, what's the best constant if we have to prevent overshoot? In other words, we want to go 2 meters, settle quickly, but not overshoot because it may cause a certain problem. So these are a couple of questions. Let's look at the procedure. First of all, program the controller, where we control the power to the drive wheels. And we're setting it so that we can go a certain distance, and the power is going to be reduced as we approach the target. So we're using a proportional control here to reduce the power as we approach the target. Number two, we set the robot up for 2 meters of travel. We're going to be using motor encoders for the feedback. Number three, we set proportional gain. In other words, let's say we use 100% of the motor power as full power, and then we'll reduce that as we approach the target. We place a robot in position, which in this case is 2 meters from the finish line, and run the program. We collect data then in terms of the time it took to reach the target and fully stop, what the final position was, where it stopped, so we can tell if it really stopped at the 2 meter position, and record any overshoot that occurred, because we're trying to avoid that for answering our second question up there. And we'll repeat these steps for different gains or different proportionality constants, decreasing down to 90, 80, 70, 60, and 50 in order to see which of these might give us the best control. So run the runs with the proportionality constant, or gain case of P. We record the time it took for the robot to stop when it thinks it's at the 2 meters. Record any overshoot that occurred, and this is the kind of data. We may also want to record any observations that were noted during the test. All right, so we're going to see that the robot travel is described somewhat like these graphs that are sketched. When we have the high gain, 100%, 90%, the robot travels toward the 2 meters, overshoots, and then oscillates before it finally settles near that 2 meter mark. With somewhat reduced, we'll get 70%, 60%, somewhere in there. It's going to overshoot less. It's going to oscillate less. It will also settle in around the 2 meters. When we get to much lower, under say 50% power, it's going to avoid overshooting, but it more slowly approaches the 2 meter target. So it takes a long time for it to get close. Now, if we actually look at the numbers, the time to reach this 2 meter target and stop looks like this. We see that at 50% power, it took about 6 seconds. At 100%, it was about 6 seconds, and the minimum time occurred somewhere in between, around 70%. Okay. We then look at overshoot, In other words, how much did it overshoot before it did settle? For the different gains, we see that the greatest overshoot was with the highest gain, the highest proportionality constant. That decreased and kept decreasing until getting down to the 50% gain. It didn't even make it to the 2-meter line, and so it ended up with an undershoot. So with this information, we can answer the questions that we posed initially. The test data show that, number one, time for the robot to reach 2 meters and stop was affected by gain, this proportionality constant, and the resulting oscillation. Okay, we knew that. The overshoot occurs in all cases with gain above 70%. So above 70%, it overshot and then oscillated and settled in. The lowest gain, 50% of full power, caused undershoot, that is, it never reached the target. So conclusions we draw from this information are, number one, the best gain, or proportionality constant, or rapid sprint to a 2-meter target is 80%. To prevent overshoot, yet reach the target, 70% gain is best. So it will just get there a little bit slower, but it won't overshoot. A gain of 60% also avoids overshoot. Its time to reach a target is slightly longer, and that may also be acceptable. So from this test that we've conducted, we can identify which conditions give us the response that best meets the requirements we had established up front. Getting there quickly, and then in the second case, not overshooting at all. So let's review where we've been here today. For assembly, we want to think ahead. Think ahead about what things will cost, what decisions will cost us in terms of time and money. We want to consider appearance as we go along and safety all the time, regardless of what our decisions are. Let's keep those in mind. We want to build in flexibility and durability, so the choices we make, we want to be sure that they give us flexibility and durability. On the evaluation side, we need to remember that we need to clearly state the questions that we're attempting to answer. We're not just evaluating, we're answering questions, specific questions. We need to explain the setup and test procedure we're going to use to answer these questions. We must gather the data and make sure we get all the data that's of importance, which also includes observations and not just numbers. We need to analyze and interpret the data as we're thinking about answering the questions. And then we need to document this process and the outcomes. Remember that our documentation is all we have to prove that we've conducted this evaluation and to show what the results are from the evaluation. All right, so to this point, we have gone through essentially all of the engineering design process. One step remaining is a risk analysis, which we'll talk about next time. But having covered the other steps, we've learned how to start with a game strategy, define needs, generate ideas, screen those ideas, construct and select concepts, specify requirements, prototype, and analyze the prototypes well enough to detail our solution. Then consider practical things in assembling the solution, and then finally evaluating the solution in the context of where it's going to be utilized. So risk analysis, we're going to look at where we have potential failures what we should do in order to make this solution really meet our needs reliably. So again, thank you for joining us today. You can find this video and others by going to my website, verdidesignlearning.com, or the Roborators YouTube channel. So please join us again next time. We'll wrap this up. And thanks to FIRST again for inspiring this kind of activity, sporting events for the mind. We'll see you next time.